Hello, my name is Brian Gonzalez, and today we will be discussing the Falcon 500 motor driver and analysis environments. This project was initially started as an effort to help out a local high school robotics team with motor issues they were encountering and things of that nature. The high school robotics team itself competes in the global first robotics competition, which I'm sure at least someone in here is familiar with, either having been a participant or having been a mentor at some point. A really good organization. Would highly recommend you to get involved with it if you're interested. Moving on. So some of the topics of discussion today are going to include the overall product description of the system, the overall system block diagram, application to the FRC First Robotics Competition itself. PWM Basics, though I would venture to guess, most people in here are familiar with how a PWM signal works, having either, designed one themselves or just kind of seen it in an application. Some hardware and software features of the actual system itself. Some video demos about the hardware and software I was working with. Additional photos conveying some of the technology that I've developed. Further development work. So, I'd be remiss to say that this project is 100% complete. In fact, I would say that there's quite a bit of development work I can still do to improve the system in general. Use cases outside of the capacity of, high school robotics, because I'm sure you could take this technology and apply it towards other cases. And then some ending content, just a little bit about myself and, some of the work I do outside of Auburn. So you can see really quickly on the right, though, the image of the Falcon 500 motor by Vex Robotics. The motor itself is a brushless DC motor that uses the Talon FX controller system housed in the back to control the speed of the motor, and that's actually where I inject the pulse width modulated signal using, I think they're called CAN wires, um, to help drive the motor at varying speeds. And it's able to be hooked up to a pretty large battery. It's like, I would say it's like a step under a car battery, but you'll kind of see it in some of the images I have later. Anyways, so the Falcon 500 motor driver and analysis environment is a hardware and software based system that uses an array of integrated circuits to drive or to generate signal activity that spins the motor at varying speeds while simultaneously collecting real-time data regarding the motor's angular velocity. The signal activity is pulse width modulated in nature and is viewable in the analysis environment using the EasyScope X software application. Now, the actual integrated circuits that I'm using are TI 555 timers that are programmed using like external resistors and stuff to be driven at different duty cycles. And when you have these different duty cycles, that tells the motor, spin fast, spin slow. It's actually really interesting. I had to call a representative from the company to be like, hey, what frequency should I be looking for? He said, around 200 hertz or so is what you want to program your 555 timers. But for the longest time, I was actually driving the motor around 500 hertz, which he advised that's way too fast for the motor to comprehend. So there was definitely some troubleshooting in this effort. Um, Now this was actually made easy with the EasyScope X software that's compatible with Siglent oscilloscope hardware. So if you have a Siglent device lying around, maybe check out the EasyScope X software to help you view in real time or you know, in instantaneous time your waveform activity on the screen. So this is just kind of an overall system block diagram where you have the push button that drives the NMOS into saturation mode, I believe, where then that current closes the relay clamp, and then the relay clamp provides power to the 555 timer itself. Now the inverter actually takes the signal, the PWM signal, and inverts it, because if you look at 555 timers, they're actually not able to go below 50% duty cycle. But when they do, well, the way to do that is using an inverter IC. And then that signal is provided to the Falcon 500 via the yellow CAN wire. and then the green CAN wire is just grounded, and the motor being hooked up to a battery. Again, we have the oscilloscope to actually view the signal activity. Um, the optical encoder itself captures the RPM based on the encoder wheel. That's actually like super glued to the shaft of the motor, and then transfers that to the PC, and then you're able to monitor the signal activity or calculate the RPM with the software interface. So what problems does this solve? Fundamentally, it assists in assessing how fast a motor will spin when coupled with a discernible PWM cycle of varying duty cycle. Secondly, assists in testing motor health and efficiency. And thirdly, assists in mitigating risk for robot brownout given the capacity to limit programmable PWM cycles on the robot. My hardware is intended to be an off, robot system where we're able to take the PWM signal activity and program into the main, processing unit for the robot. Now, the actual like robot itself uses something called like a Robo Rio to generate the signals to drive the motor. So that helps us at least gauge where, how fast the motors are going to spin per the PWM and avoid things like brownouts. Now I have a quick video to show you of the actual robot in action. So you can see it zips around pretty quick. And so it probably does consume a lot of power, and browning out is a potential risk. So PWM basics, if you're not familiar, basically whatever percentage of duty cycle you have high is what the load is going to encounter. So say you have an LED that's being pulsed at 50% duty cycle. Well, it's effectively going to see 50% of whatever power source is being provided to it. So if it's 4 volts, then it's effectively going to see 2 volts at 50% duty cycle if that's the system you have going, and thus it'll adjust its brightness, its in light intensity accordingly. So I actually designed a printed circuit board to house all of this technology. This is a bit more of a hardware version of the block diagram I showed you earlier. So, you have the push button itself, the DC to DC converter, an LED to show that that state is on or it's active, the NMOS device to drive the relay coil to turn it on and to provide power to the actual 555 timer presented here. There's various test points to be able to look and see like, okay, where, what's going on in the circuit. Is the circuit over here, is the relay state here, or, is the push button state there? This helps, look at this test point actually helps look at the signal activity produced after the inverter. This actually says do not populate, but in like a standard situation, it would actually be, programmed with various resistors. Same thing here with the capacitors, and so the output would be generated here. You can see timer 1, and that would be ultimately taken to the motor for processing. My apologies. So the 555 timer, this is, a sample, just a quick snapshot of what the pulse width modulated duty cycle will look like. The optical encoder, so you can see the optical encoder here, the AEDB9340-B13C optical encoder by Broadcom. Now, if I had to go back and change something, I actually would try to select a little bit more reliable of optical encoder. This one, was kind of iffy sometimes on whether it would work, and I have some theories as to why that's the case, but I haven't narrowed it down exactly why. So that is actually listed as like a way I think I could improve this hardware if I really wanted to. So you can see this is actually the signal activity produced from the optical encoder when it's spinning in real time. This is the x-axis cursor measurement, and then there's the y-axis. You can see the x-axis has a kind of a frequency, well, I should say a period of 3.92 milliseconds, and the amplitude measures around 5 volts because it's supplied by a 5 volt power power source you can see here, VCC, but it operates off a single 5-volt power supply. One thing I actually did, that I would change is roughly taking the power supply and providing it from a separate system than the actual 555 timer IC, because I think the current that was diverted to the optical encoder may have caused issues. You can see the software set up here in MATLAB. This helps me calculate the angular velocity per the the waveform period. One thing too that I provided in the table is okay, for what duty cycle, what is RA and RB going to be? Now RA and RB, if you look back at the situation up here, this array of resistors is going to be RA, and this array of resistors down here is going to be RB. That helps drive the motor at varying duty cycles, as you can see in the leftmost column. So 25% is pretty much going to be full reverse, 50% is going to be full forward, and then 35, 40% is where it's going to be operating at a pretty slow rate relative to full forward. I have a quick demo here to see, the actual oscilloscope and the optical encoder working in tandem. It's not the best because you really can't see the motor spinning due to my hand kind of blocking it. I actually had to hold the optical encoder in place. But here you can go ahead and see the motor spinning. Well, not the motor spinning, but the actual waveform being generated. So you can see the square wave activity taking place on the oscilloscope. Some additional photos. Here's another view of the setup. These are pretty cool. These are called like decade boards, where that helps me, define like RA and RB, but not having to like individually find like discrete resistors, and just being able to use the decade boards and swap those values out rather quickly. These are the wires that the optical encoder would attach to. You can see the little optical encoder will attach to the shaft of the motor. Here's the actual circuit. It's a simplified version of the circuit I showed you above, where this one just has the push button, the timer, and the inverter. But the inverter is actually just like a NAND gate that I was able to just wire and hook up, and producing the signal that then is fed to the motor. Here's the optical encoder. You can see it's pretty small. It's not, but a little bigger than a quarter per se. Here's a version of the PCB that I designed that's, houses about 12 different states of it. And then the states are all fed to a rotary selector, and then they're all fed to the output. So you can hook up 6 motors, given that there's 12 positions. The rotary selector was useful because it helps me ensure that the signal is not going to backflow, from one IC to another. So, if state whatever 10 is on, the signal being output won't backflow into state 11 and potentially damage the IC. Here's the actual printed circuit board that's been manufactured. It's been partially populated with some passives like resistors and capacitors and things like that, sitting on top of an ESD bag. So once I am able to populate this, I'll probably take it to the high school and be like, hey, here's what I designed, here's how it works, and let's try to get it set up and make it work for the robot. So further development work, I want to improve the software interface to display like real-time data, like a speedometer, preferably in like a digital format so that it's easy to read. But I know LabVIEW and MATLAB provide like almost analog gauges for this stuff, which is kind of interesting. I want to do a situation where instead of the decade boards, I have potentiometers that do the same thing as the decade boards, but I want them to be physically housed on the PCB. That would be a hardware improvement. Separate power terminals for the optical encoder, because I think that caused some issues. Signal conditioning circuitry for the optical encoder to make it smoother signal. Inserts for Arduino Micro or other development boards, because once I'm able to get the Arduino and the signal conditioning circuitry figured out, then I can go ahead and um, start doing some of that more real-time data acquisition. Finding an alternative optical encoder may be a potential issue to overcome. Low ohmage power resistor to go ahead and assess current draw from the motor battery. Acquiring a proper mount for the optical encoder as well, because you can see I had to hold it in place. Some other use cases, though, really quick, are motor design companies like Linear Labs. They're actually based out of the same area I live in, so Fort Worth, Texas. They do some really cool stuff with smart motors. But industrial manufacturing, we talked about, the biggest application of robotics and advances is in industrial manufacturing. Vehicular transportation, so obviously, with EVs being on the climb, this could be a situation where, if you extrapolated this to a bigger system, that could prove really useful for an EV company. Robotics organizations, so, like an FRC team or even like a corporate entity. Just kind of to close out, this is, just to put a name to a face, or a face to a name. This is me. I graduated 2019 from Auburn, work at Lockheed Martin, mostly in the capacity of PCB design, electronic testing, and firmware AI development for corporate-wide R&D efforts, mostly supporting F-16 Fighting Falcon. Like I said, I volunteer for a local FRC team. Um, Ultimately, my career interests do lie in technology like robotics and RF hardware and power, and things like that. And so, yeah, you can find me on LinkedIn if you're curious. And thank you for listening to the presentation today. I hope you all have a good week. Thank you.